we have seen that causes may be due to the material variation, or due to abrupt changes in the cross section, that is discontinuities. Surface irregularities and other kind of things because of the manufacturing considerations. And because of this causes, the stress concentration is inevitable. And especially if it is brittle material, it is very important to consider the effect of stress concentration, both static and dynamic. However, if you are only dealing with ductile materials, dynamic loading alone is important. And we have seen some simple machine elements which are subjected to different kind of stress concentrations. Sometimes we try to mitigate it through some kind of manufacturing things like either drilling a hole or giving a fillet or giving a rounding off or kind of removing some material. These are the kind of ways we kind of mitigated the stress concentration factor to a certain extent. So stress concentration by several methods like removal of material, rounding off, rounding the corners, drilling holes, etc. Now, even after that, sometimes the discontinuities in the stress lines do occur for a longer time. In those things, what we generally do is we have to give the designer has to consider the effect of stress concentration in the designing. In that, what we have done is we have followed 4 tabular charts. One is a plate, a flat plate with a hole of diameter W and D by W. We have shown that for a far field compression or tension, a tabular chart has been provided. This is the first case. And in the second case, there is a flat plate. And again, it undergoes a change in the thickness. Now, if it has a root radius r, and this is capital D, and this dimension is small d, based on d by d ratio and r by d ratio, this is a flat plate with a shoulder and a fillet at the shoulder. We have given the stress concentration factor. Then we talked, this is subjected to again tension or compression. Later, we took a kind of a circular shaft, and again it had abrupt this is circular cross section. It's a shaft, circular shaft. This is also a circular shaft. And we showed that depending upon this capital D, by small d and a root radius of r, d by d, r over d, when it is, and this is for tension, and d by d, r over d with bending m was another consideration we have given. So let me just summarize those tables here again back. This is the first case when you have W by D, and based on this we have given the stress concentration factor. And the second case is flat plate with a tensile load having a shoulder. This is the second case. This is the third case when a circular shaft with a shoulder subjected to axial tension and finally the same configuration subjected to bending. You can see that the stress concentration factor in this case is dependent upon d by w the kind of maximum stress concentration factor. And as we said yesterday, we defined Kt as sigma max by sigma naught, where sigma naught is the kind of stress, average stress that is obtained from the elementary equations like P by A or My by bending as well as torsion and other kind of stuff. So with this, what we have done is we solved 3 different problems and showed the usages of these things and how the stress concentration has to be taken care using these kind of charts for a given configuration. Okay. Now today what we'll do is we'll go further into the dynamic loading, and the topic which we'll study today would be under the fatigue loading, so fluctuating stresses. So now we are talking about design for dynamic loads. So a dynamic, which is like it can be a repeated loading or variable loading or load. All these things comes under dynamic loading and is one that varies with time, and also you need to understand that it also involves also has inertial effects. Okay. Now, machine members can fail under cyclic loading for large number of cycles, even if the stress levels are much lower than the material ultimate strength or even yield strength. So if you know that for any stress strain curve, we know that this is SUTS and this is SYT. Let's say it is under tension. Now, if it is a static loading, if your design is based on yielding, then this is the failure load. And if it is kind of final strength based of design, then it is up to SUT or S rupture, depending upon whatever you are kind of designing into the picture. Further, when you are loading in the specimen, it is only loaded monotonically. That is, only loading is there. There is no unloading part is carried out, and hence the failure is designed for the maximum load at this given point of time. However, when you do fluctuating loads, that means once you go to a value of, let's say, sigma 1 and unload it back to, let's say, sigma 1 and unload it back to minus sigma 2, that means you can also go to kind of negative kind of loading. So when you go back and forth, even you are well below this SYT, after some repeated number of cycle, it may be high cycle as the very large number of cycles, or it can be low number of cycle, but after few number of cycles, even though operating at a much less than these two things, the material tends to fail, and this failure is called, so this kind of is called fatigue failure. Further, about 80% failures of mechanical components are due to fatigue failures resulting from fluctuating stresses. So during fatigue, what happens is, so fatigue failures start at razors, or as we studied yesterday, at stress concentration location, which may be either mechanical or metallurgical in nature. The examples are, you know about automobile axles, springs, turbine blades, airplane wings, gears, rail wheel, bridges, etc. So this is the kind of thing. In the today's lecture we'll understand what is the fatigue and how to create a fluctuating load, and what are the types of nomenclature that are involved in the fluctuating stress component. And we'll also talk about fatigue strength, which is, and also like which is like SN curve, endurance limit, and other kind of things, important topics that are required for a mechanical component design for fatigue cases. In most of our, if you look at the mechanical components we are generally designing, we design it such that it can be used multiple times. That means whenever you are using not for one single time, it is most obviously is kind of undergoing a fatigue things. For location A to location B. So that means during a takeoff, it is subjected to kind of heavy loading. Suppose it has a minimum kind of a region, and again when it is kind of landing, it has a very big cycle, heavy loading it has to take. So from, you can consider as landing, takeoff, cruise, and landing is one cycle. And no matter what might be the length of the cruise can be bigger or longer or something like that. But every time a kind of plane kind of takes off and lands down, so it is like a one cycle. So in that, you know that you are operating this kind of a plane for multiple things. On subjecting it in this kind of heavy loads during takeoff and landing, what happens is the wings and certain components are subjected to fatigue loading. So that is one example. Or if you consider an automobile, for example, we know that whenever we start a kind of an automobile, that is the kind of starting cycle, and its cruise time can be, or its operating time can be large. Again, when you kind of switch it off, because of this the components may be, the engine parts may be heated up, so it gets again cooled down. So there is a heating cycle, there is a kind of a constant region, and then it's a cooling region. It can give you thermal stresses, or it can give wear and tear, it can give several different kind of loading under the operating conditions. But every time you operate, you consider it as one single cycle. Okay, so that is kind of things when we are talking about the things. And if you consider, for example, bridges, So every time a kind of vehicle pass by, so it can be one full cycle, and this kind of can be repeated as many vehicles as it goes on. So we generally design all these things to sustain this kind of loading for very large number of cycles. We don't want it to operate to fail after few cycles. So we want to design so that it can still take intended life. So the life can be in terms of years, but when it comes to fatigue, we generally talk about number of cycles. So from the cycles, one can even kind of back calculate it. So this is quite an important topic, especially for our mechanical engineers, because most of the time we day in, day out, components we design are used for daily purposes. For example, even if you take a laptop or a desk thing, whenever you switch it on, all the kind of packaging inside the motherboard and other things are kind of started taking the load. At the startup, it will have higher load and it will be kind of kept constant. And again, when you shut down, it will have a kind of unloading kind of a cycle. So, and you know that you do switch on and off for several times. You don't switch it off once and then say that it should last. And once it is off, will not throw it away. So because it is intended for multiple purposes on and off. So each one is a kind of a cycle. So not only in mechanical, there are several places where you see fatigue loading that comes into the, or fatigue is there in the in the service conditions of the components that you are designing for. So let us kind of quantify our loading first, and then we'll talk about the fatigue strength at a later point. So quite a few definitions we'll start with today, and then we'll go up to how to determine the fatigue strength as we go along. The first definition is fatigue failure. It is the phenomenon leading to fracture under repeated or fluctuating stresses that are less than the ultimate tensile strength of the material. So for example, we can even give a biomechanical example. Let's say a sprinter, he can, or an athlete who can kind of do a marathon run like 52 kilometers, right? His endurance is there for that kind of a thing. But let's say if he runs every day, let's say 20 kilometers, 20 is much less than 52. If he runs 20 or let's say 30, or even 10 for continuously for 100 days, and at one point of time he breaks down because of fatigue, because even every athlete doesn't do kind of workout every day. They kind of do workout for 2 days or a day and then take a rest, and again they do it. Otherwise they'll be undergoing through this kind of a fatigue. Okay, the same thing, the materials also is subjected to the similar kind of things. Even though his maximum thing is for 52 kilometers, he would kind of crumble if he has kind of running every day for 30 kilometers for 100 days. Then one fine day he would break up. So that is the thing. And sometimes he may not, and that is the limit, is called his endurance limit. We'll also come to that part. So what is the safe number of kilometers he need to practice so that he can last forever? That is also there. That is called endurance limit, as I said. So anyway, we'll come to those things. First thing is the fatigue failure, which we have done. Then little bit about this fatigue failures are fatigue are progressive in nature. That is, they begin as minute crack that grow under the action of fluctuating stress. Then, in the fatigue failure or the fatigue fracture, there are three stages. Three stages of fatigue. The first one initiation. So the surface scratches and defects due to manufacturing or because of poor design are the initiator. Next is propagation. So the loading itself, the repeated loading, increases size of the crack or the defect. Then is final fracture. So when cracks have grown in sufficient size, then the final of the fracture in the fatigue cases. Next is we'll talk about fluctuating stresses. So let me show some kind of pictures of type of fluctuating stresses. So these are several types of kind of fluctuating stresses. So in here, you see that it has started at non-zero value and it has so much roughness of the cycle, variation in the cycle. So it has a kind of a low frequency and as well as a high frequency oscillations that are both there in this, whereas in this one it is only kind of a low frequency that is there, that is present in the thing. Further, in this case you can see that this is the zero and this is the whatever is the kind of stress, and here the starting point is a non-zero stress. The starting point is a non-zero stress, and this is the lowest point is negative, highest point is positive. In here, the highest point is positive, the starting point is also somewhere positive, and the sigma min is also positive. All are above a zero value. That is both, it's a fluctuating, but it either it is completely tensile or completely compressive in nature. Whereas this case, it goes from the kind of non-zero state of stress to a tensile value, and then it comes back to some kind of a compressive value, and then it fluctuates in the same thing. Now, here it starts at a compressive point and goes to kind of maximum tensile and falls back to kind of maximum compressive. Similarly, it starts at some value here, goes to some maximum value, and the minimum matches with the zero loading. So this is another kind of loading, or this is only one single cycle. There can be multiple complex cycle. This is a complex cycle. So in this, it goes up and down, and again it goes up and down. And from here, at this part, this picture again repeats in itself. So this is, and here in between you can have much more things. So in fact, if you look at the plane landing or takeoff and intermediate kind of things, the flight of a plane, you can see that the wings are subjected to spectral loading. That means you can see different variations of the intensity in between, but one that such kind of things is one given cycle. Anyway, in here you can see in the thing, here in case the mean is matching with the zero, the maximum is kind of this one and the minimum is exactly in the same value. So firstly we'll study about these things, and then we'll have an off kind of a mean, and we'll study about the other things. So let us have a definition about fatigue strength. Or anyway, I have to, before finishing the, let us, one few couple of definitions I need to give here. So sigma mean is defined as the maximum value plus a minimum value divided by 2. So this is the maximum value, this is the minimum value, the average of that is your mean. In everything, your dashed line is the thing. And sigma amplitude is given as sigma max minus sigma min divided by 2. So from here to there would be your sigma amplitude. Okay. So these are the different kind of things. In each case, you have different max and min. You will have different mean. You have different amplitude and other kind of things. So this is, as we said, there are complete reversals if maximum in the positive as well as in the negative are same. Otherwise, there will be not complete reversal that would be happening. You can have complex cycles compared to the simplest sinusoidal form, and all other things can be possible when you are subjecting it to fluctuating stress. The next topic is fluctuating strength or fatigue strength. So fatigue strength is the maximum reversed stress that a standard specimen can sustain for the given number of cycles without fatigue. So it is the kind of if you have even a small magnitude more than that, the reverse stress, then it will lead to kind of failure um, because of the fatigue failure. So the value that is helping us not to fail under fatigue failure is called as fatigue strength. The statement of fatigue strength value must be always accompanied by the statement of number of cycles. Further, fatigue strength of a material can be obtained from SN curve generated by testing on standard specimen. So here where S means stress, N is the number of cycles, so such kind of SN curve has to be generated. And one thing is generally this fatigue specimen stress strength is determined on standard specimen, and for each kind of um, data point, or let's say for a given state of stress, you need to kind of use one specimen. So the fatigue strength determination is a kind of first time consuming process and also a lot of material consuming process. But without doing these things, it is very risky to operate, because most of the times if we just do under static loading, it is still conservative. But what happens is even before it does its complete, let's say 6 years of service or 10 years of service or 10,000 number of cycles, if it fails, then its intended service, I mean, let's say if you're designing for some number of cycles and if it is not sustaining it, that is also a failure. So failure is not only kind of is like when sigma is based on strength or stiffness, but you need to also understand that it should maintain the strength and stiffness over desired life. So in order to design the life of a thing, one has to come to the concept of fatigue strength. Okay, to determine the fatigue strength, SN curve will help you a lot. So in we will see that how this SN curve can be developed using a kind of experimental technique called Wöhler's diagram. So in this, this is kind of a setup of Euler's diagram. So we will walk you through how this thing is there. So you have, this is your standard specimen, which is subjected to kind of torsion, and it's connected to electric motor, and each revolution counter is measured using the revolution counter, and the weight is attached to kind of give the loading. Okay, so let us kind of write it. So completely reversed sinusoidal stress are applied by applying so there are machines which can even apply a torque kind of things, especially if you're keeping a transverse weight. This will result into the pure bending. So this would be bending it in this form. So these weights are used to create the thing, but there are alternative machines which create a torque. So these things can also be subjected to a shear loading, and in this case, with the weights, transverse weights, it will kind of create a pure bending moment. Okay, and number of solutions till the appearance of first fatigue crack is recorded for each stress amplitude SF. So the results obtained are plotted with n on horizontal axis and the stress amplitude at the first failure or first appearance of crack on the vertical axis. And in generally, this is plotted under a semi-log plot semi-log, or it can be both log paper to emphasize the bend. So we will give you an example of this thing using a picture. So let's say if you're operating any given sample, let's say at 10 to the power of So let's say uh, uh, we want to operate something at 100 SUF. So, or we want to operate it at 100 Newton per mm square. If you operate at 100 Newton per mm square, you can see that under this log plot, it comes out something close to 900 kind of a cycles. Now, at the same time, if you operate very close to SU2 itself, it will just break at only one cycle, because at the first cycle it will kind of break. Now similarly, if you kind of have it, let's say this is 900, this is 800, 90 and 80, at 80 Newton per mm square, if you do, it will come close to kind of 800 to 900, 9000 cycles. Similarly, if you do operate at 50, you see it reaches a plateau. That means a value anything below the 50, it sustains more than 10 power 6 cycles. Generally, in the design purposes, we just take a 10 power 6 as the kind of um, life or an infinite life of the material. Okay. Further, if it fails less than 10 power 3 cycles for any given component, that is called it's a low cycle. And if the life is more than 10 power 3, it is called a high cycle. Okay. And if you are designing for a finite life, that is, it happens from this place to this place. But if you are designing for infinite life, so infinite life is synonymous to having 10 power 6 number of cycles. So if you are designing for kind of 10 more than 10 power 6 number of cycles, for example, this is a case for a stainless steel subjected to pure bending, then you can clearly see that if you are loading much less than 50, then at 40, let us say at 40 or 20 or whatever is this value, at all the values below this thing, its life is more than 10 power 6. So if you take 10 power 6 as the infinite life, because 10 power 6 cycles are really huge in number, so based on that, we can clearly say that uh, 50 in this case is an endurance limit. So anything below 50, it can take infinite life. But anything above 50, its number of cycles before a fatigue failure occurs is kind of less than 10 power 6, less than 10 power 6 number of cycles. So now, based on this picture, we will define something called as endurance limit. The fatigue or endurance limit of a material is defined as the maximum amplitude of completely reversed stress that the standard specimen can sustain for an unlimited number of cycles without fatigue failures. Further, for ferrous materials like steels, SN curve becomes asymptotic at about 10 power 6 cycles, indicating stress amplitude corresponding to infinite number of cycles. Similarly, for non-ferrous materials and alloys, this curve does not become horizontal and continues to slope down even after 10 power 6 cycles. For these materials, fatigue strength SF is reported at a specific number of cycles. So with this, we have understood what is about our fatigue strength and how much it can take. So what we'll do is in the next class, we'll introduce something called as notch sensitivity, and then because of presence of stress concentrations and notches and other things, this endurance limit will again further fall down, because the endurance limit what we have shown is for the standard specimen, but once you have service sports, or we have roughness, or if you have dynamic loading, if you have several other features like that, like the load, size, surface preparation, and kind of type of loading, this and the notch stress concentrations, all these things would further lower the kind of endurance limit. So this, the corrected endurance limit is like kind of some form of giving a safety factors for the design based on the fluctuating stresses. This concept would be new, so what we'll do is we will try to do it in the next class by introducing what are the corrected forms of things and for what corrections we need to make, and then we'll go through couple of problems to solve the things. Further, what we'll do is, so far we have done endurance limit is with a notion that our mean is at a zero value. That is, it's a complete reversal of the load. But at times what happens, there will be non-complete reversal of the load. In those cases, the behavior of the material is much more different than what we see in the complete reversals, and then design for the fluctuating stress with non-zero mean has to be done by creating an offset or something like that. So which will be again doing it in the subsequent classes. With this, we'll end today's class. In the next sign for, as I said, non-zero mean, and then we'll end the chapter on the fluctuating stresses.